All right. Hey everyone. My name is Kurt, and I also go by the name Faze. You can find me on Twitter. My handle is Love the Wired. I work as a security engineer and researcher in blockchain at 12 Bits. And for those of you who don't know, at 12 Bits, we work with some of the industry's leading teams running security reviews for their protocols. We also make an effort to contribute to open source projects with static analysis tools, for example, Slither, fuzzing tools such as Echidna, Medusa, and created securecontracts.com as a resource. And today I'll be giving an introduction to ERC-4337 Account Abstraction using Alt-Mempool. Account abstraction has gotten quite a lot of visibility lately, especially with Vitalik giving a dedicated talk at ETCC last month. If you haven't seen it, it's a great resource for seeing what's been done so far and the challenges that we face. And in this presentation, I'll be going more into depth on the functionality and the security assumptions surrounding ERC-4337 in particular. So let's jump in. As an overview for today, I'll start with the motivation on ERC-4337. Then I'll go through some of the EIP history, what's been done so far, and what do we have today. I'll jump into some of the terminology and the specs. Then I'll give some examples of how you can use ERC-4337 and talk about some of the security considerations that went into the design of the spec. For that, I'll go through two different flows, and then I'll talk about some additional features, and then I'll give some final thoughts. So first, why do we want account abstraction? So the idea is that we want smart contract functionality for accounts. Currently, we have this distinction of smart contracts and EOAs. EOAs meaning externally owned accounts, so accounts that have an associated private key and accounts that can basically sign transactions and send them on chain, whereas smart contracts can contain code, but they don't have an associated private key, and EOAs currently cannot have any code, so they cannot have like any additional logic tied to the execution of transactions. And if we had this kind of functionality for EOAs, we would be able to batch transactions. We would be able to have like multi-sig wallets, social recovery. We could have alternative signature schemes, then also gaseous transfers and private withdrawals, for example. So let's go through some of the EIP history, starting out with EIP 86, originally created by Vitalik. We have abstraction of transaction origin, which is dropped now. However, it introduced the trusted forwarder concept. It also highlighted the need for a create2 opcode, basically a method of creating new contracts independent of the current contract's nonce. But that create2 was not introduced in that EIP. That was a different EIP. Then I'd also like to mention EIP 2771 meta transactions, which is live. It's not necessarily related to account abstraction. However, it introduces a bunch of concepts that are used today, which or features that we would like to have in account abstraction today. And meta transactions also has this concept of a trusted forwarder that is able to pass a custom message sender and message data to another contract. A restriction with this EIP is that it's only possible to integrate it for future contracts, so it's an ad hoc solution, and also the critical logic is left up to protocols to include. And we see that there are often like centralized relayers and upgradable trusted forwarders. This is because like of the surrounding infrastructure is not part of the EIP yet, but we also have great infrastructure by OpenGSN, Gas Station Network, and Biconomy. And another EIP is EIP 2938, Account Abstraction, which is also dropped. It tried to introduce a new transaction type, introduced two new opcodes, nonce and pay gas. However, due to significant changes in the protocol and like open questions and considerations, it got dropped. And I think it also hadn't encompassed some of the features of 2771 that we wanted. There's EIP 3074, which I want to quickly mention, introducing auth and auth call opcodes, which is currently under review. For those of you that know delegate call, so delegate call allows you to execute the code of a different smart contract inside of the current context of the current contract. Auth and auth call opcodes would allow you to execute the code of a current contract inside of the account of an EOA. So interesting EIP. However, I think Vitalik created a post about it saying that basically, in terms of account abstraction, it's heading into the wrong direction because we're building on top of this distinction of EOAs and smart contracts, whereas we should try to remove this distinction instead. And it doesn't allow for things like social recovery or alternative signature schemes, and it builds on top of using these existing ECDSA signature schemes. We have also EIP 7377, which just got announced recently, I believe, a migration transaction, which allows EOAs to send a one-time transaction to deploy code at their account, which is currently in a draft stage. So I'll introduce some of the terminology, which is inside of the ERC-4337, and talk about some of these specs. So as a quick example, we have Alice, who wants to send a transaction from her wallet. In this case, the wallet will call a contract account or smart account. This is a smart contract wallet owned by Alice, and a transaction in this case is called a user operation. It's a kind of internal transaction sent from the contract account. You can think of it as a transaction which is going to be wrapped inside of a different transaction. We have the concept of a bundler, a relayer, in this case, Bob, in the picture. I won't make the distinction between a bundler and a relayer. They could be separate entities, but here we'll just assume that they're the same. So the bundler takes a bunch of user operation, bundles these together, and then sends them on chain through the entry point contract. And the entry point is like the main, as it says, the entry point, which is able to execute the bundled user ops. We also have the concept of a paymaster. A paymaster is able to sponsor transactions for contract accounts. So imagine Alice doesn't have enough gas to pay for the transaction. Paymaster can step in, pay upfront, and get reimbursed by Alice. And then also alt mempool, basically meaning the mempool is a peer-to-peer mempool propagating these user operations, and alt mempool in this case meaning alternative mempools, meaning there could be different kind of specs that have like separated mempools. For example, we'll see that there are many restrictions for these kind of user ops, and perhaps we would like to have a separate mempool with less severe restrictions. So the EIP or ERC-4337, in it, it defines a user operation and interfaces for a bunch of different contracts, such as the entry point, the wallet, paymaster, aggregator, and it also heavily restricts the behavior for these contracts. And we'll see in a bit why this is important, or why this is such a big part of the ERC. It also defines the peer-to-peer permissionless alternative mempool that we're propagating these user ops. And the whole spec, a big part of it just aims to minimize any kind of DOS attack surface. So this is a ERC that not only contains specs for on-chain code, but also a lot of off-chain components. And the good thing about this ERC is that there is no consensus level change required. So this is something that we can implement today, and we don't have to wait for some kind of hard fork, which would really require so many more considerations. And this is something that we can start using today, and we can iterate on top of it, and we can see what kind of challenges come up and adapt the ERC. So yeah, as Joaf Weiss from Ethereum Foundation said, this is a good first step for experimentation compared to a native implementation, which would just need so many more considerations. And this is because the specs are just so difficult and complex to encompass all of the features. So what does a user operation look like? Here we have an example of the struct in Solidity. It's fairly similar to transaction. We see there's some additional fields. For example, there's the bytes init code field, which contains it basically contains the code to create a new user wallet. So inside of a user operation, if the user so desires, they could create a new initial wallet. We also have a field Paymaster and data to specify a Paymaster and to pass on some additional data. We also see there's a distinction between the verification gas limit and a call gas limit, and we'll get into this distinction in a bit. So this is somewhat what the entry point interface looks like. It's simplified. So the bundler, the important operations for the bundler are handle ops. So this is the function that is executed for running all of these user operations. The bundler also needs to be able to simulate the validation step and to simulate the handle op step, or simulate the execution step. The Paymaster needs functions for stake management. The wallet needs functions for a deposit management. Sorry. So let's get into a specific example of how you would use ERC-4337 and talk about some of these security considerations. So in this is a simple relay flow. So Alice would like to execute a transaction from her wallet or a user op in this case. So in this case, Alice creates this user op. She signs it off chain, submits it to the mempool. Bob, the bundler, picks it up, bundles a bunch of these user operations, submits the bundle on chain through the entry point contract. Alice wallet, in a first step, verifies that this user op is allowed to be executed inside of the wallet, and Alice then reimburses Bob through the entry point, and then the user op is executed. So why would we even want this in the first place? Like, why can't Alice immediately send a user op herself? Well, in this case, we don't want to make any assumptions on Alice perhaps containing a private key. So inside of Alice wallet, there could be arbitrary logic for verification, for verifying that this is a valid transaction. So we could imagine that there is some kind of post-quantum signature scheme being used in Alice wallet. And for that, like I mentioned, we don't want to make any assumption on what kind of signature verification scheme Alice is using. So in a bit more detail, and looking at more detail of the single steps, we have first the off-chain phases, where Alice signs the user op and broadcasts it over the network. Bob picks it up, validates it, and simulates the user ops. Bob checks for the EIP adherence of the validation call. So during the validation step, there are a bunch of restrictions, which we'll get into in a bit, and these all need to be checked by Bob and verified. Then for looking at on-chain operations, in the first step, Bob submits the bundled user ops in step 1. In step 2, the entry point checks whether Alice wallet accepts the user op. And here, the Alice wallet could have a deposit inside of the entry point contract in advance, or Alice wallet can in step 2 send and deposit back to the entry point contract. In step 3, the deposit is deducted. This is something that happens inside of the entry point contract and doesn't need any external call. In step 4, the user op is executed, And then in step 5, the bundler is reimbursed and the wallet is refunded for any unused gas. And this all happens inside of the entry point contract again, inside of the deposit. If Alice wants to withdraw this deposit, she can at a later point. So let's get into some of the security considerations that Bob the bundler might have. So Bob is primarily concerned about any DOS attacks. You could imagine a simple scenario where a malicious user just sends in a bunch of invalid user operations. Bob spends a bunch of resources and compute verifying these, only to see that they are invalid transactions, which is a big problem. Bob also takes on the economic risk. So Bob is the one who sends the transaction onto the Ethereum blockchain. He has to pay upfront for the gas. If these operations fail and Bob is not reimbursed, then he's the one left with the economic loss. So that's why we have the challenges. We would like to minimize the risk of any bundler unpaid work. And we'd also like that the off-chain simulation and the on-chain execution, that they should be equal, meaning that if Bob simulates the user op off-chain, once he executes that user op on-chain, we also, like, if it succeeded off-chain, we also want it to succeed on-chain. So that's why we have the following security measures. We split up the whole process into 2 phases. We have a light verification phase and a heavy execution phase. So what do I mean by that? For the verification step, so this is the step where the signature is validated, we have a maximum gas limit. This is not something that I think is necessarily enforced by the protocol on-chain. However, it is specified for the peer-to-peer network, and this is also an example of a spec that could be changed for an alternative mempool. So say there is some kind of alternative or some kind of reason for increasing the gas limit, then you could have another mempool which allows for a higher limit. We also want to restrict the use of context-dependent opcodes in the verification step. So you could easily imagine that Alice, if Alice was malicious, includes some kind of code that says, okay, after a specific timestamp, after that timestamp passes, the transaction should revert, or the user op should revert. Bob simulates the transaction on-chain, off-chain. It looks good. He sends it on-chain. The timestamp passes. The transaction reverts. Bob isn't paid, and Bob is at a loss. And for that reason, we disallow any context-dependent opcodes. So timestamp, block number, block hash. They're all forbidden opcodes inside of the verification step. The execution step, so where the user op is executed, does not have these restrictions. We also restrict the storage access during the verification step. So Alice is only allowed to access storage associated with her smart contract wallet. Yeah, and Bob also needs to simulate all of these user ops, renew them on every new block, just to make sure that they're current. And another restriction is, for example, that Bob is only allowed to include one user op by a particular wallet per bundle. And yeah, basically we want to mitigate the risk of having a multi-invalidation. Basically, we want to disallow one transaction invalidating n user operations. And that's also why we disallow multiple different user operations accessing the same storage slots. So, and this is all stuff that Bob has to check off-chain. Bob basically runs a debug trace call and has to make sure that all these these restrictions all are adhered to. So some security considerations for the user. The user only requires trust in the entry point spec adherence. So what does this mean? The user op should only be executed if and only if the verification succeeds. And this is because the Alice wallet grants the entry point arbitrary code execution, or arbitrary call execution, which basically means that if there was any kind of vulnerability inside of the entry point that would allow anyone to make calls inside of Alice wallet, this would be very bad. Then there are some smaller assumptions or security considerations that we make. For example, that the entry point enforces the signature deadlines, because this is, again, the wallet itself is not allowed to access context-dependent opcodes, so checking the timestamp is not allowed. This is something that's done inside of the entry point contract. And then some smaller assumptions like that there's correct accounting for unused gas, and then some like implementation-specific assumptions, like that the provided hash by the entry point actually equals the user op hash, but that's more details. But all of this shows that the entry point is a contract which is trusted by many different users and with potentially all of their funds inside of it. And the entry point functionality requires high assurance. It needs many eyes on it. It requires a lot of testing. Yeah. So what does it actually look like to create and sign a user operation? Here's an example inside of Solidity. We declare the struct in memory. We fill out the required fields, so sender, nonce, call data, gas limit. And then we basically take this user op, we hash it and have to sign it. So op.signature is not filled out yet. And I mean, we could hash it ourselves, but you can also just simply call entry_point.get user op hash, pass in the op, you get the hash returned. And then this hash is signed as a Ethereum signed message, and then it is packed inside of the variable op.signature. So Bob off-chain has to simulate the validation, and this call always reverts. And inside of the revert, inside of the validation result, so this is basically the revert data, this can be decoded into a struct, and then you can access, or you can get more data outside of this. As mentioned before, this I mean, you wouldn't necessarily run this as a call in Solidity like this, but this would be done with a debug trace call, and because all of these EIP 4337 spec adherence must be checked. Okay, I see I have a question that just came up. Okay, so the question is, value is not allowed around the call opcode. How would you deal with subscription payment? Okay, subscription payments with value. So I believe the restriction only applies to the verification phase. So if there was some kind of subscription payment, that restriction shouldn't be applied to the execution phase. Yeah, I hope that answers the question. And there's another question regarding the storage access rules that are limited to the account. Is there any way to bypass this rule? That's actually a good question. I'm not entirely sure how it's checked. So basically, the idea is that any storage slot associated to an account is, for example, a value inside of a mapping. So be it some kind of balance inside of ERC-20, we see it's a mapping from a account to a UN256. And to access this storage slot, we basically take the account address and the slot, and we hash it together. And by accessing the result of that hash, which contains the account inside of the hashing, we know that it's a storage slot that is associated to that account. And is there any way to bypass this rule? So I'm not sure if you're thinking of like a way to kind of break this rule, or if you're thinking of the question more in terms of if so there is a way that you can still access other kind of storage slots if you as a user, the wallet actually has a stake inside of the entry point contract. So I'll go into a bit more detail in that later, but basically we have this idea that as long as the entity is staked, we can kind of relax some of the restrictions. And again, there's also this idea of alternative mempools that can have different kind of specs. Yeah, okay, I'll jump further. So, okay, now that we have created this user op, and Bob has simulated everything, and he has seen that everything is fine and everything executes and validates, Bob takes a bunch of these user ops and puts them inside of an array, and then basically to execute them calls entry point.handle ops, passes in the ops, and can also specify a beneficiary to receive the refund. And now we're introducing a paymaster, and yeah, let's go through the flow with an included paymaster. So in this case, again, Alice creates a user op, signs it, sends it to Bob. Bob submits the bundled user ops on-chain inside of the entry point. And now Alice Wallet verifies that it allows this user op. The paymaster also verifies that it allows sponsoring Alice transaction by paying the gas upfront. Then Alice gets to execute the user op, and then basically the paymaster is reimbursed by Alice Wallet. And like, why would we want this kind of scenario? So this is the use case where Alice, for example, has some kind of ERC-20 token. She has basically some value. However, she doesn't have any native gas token. So in this case, so this, you could think of the scenario, for example, when bridging from one chain to another, you might bridge some token. It's some kind of, it ends up being some kind of wrap token. It's not the native token. And for that case, you would want to kind of swap this token for the native token to be able to use it, but you kind of need this intermediary paymaster in between. And we'll go into some of the details in a bit as to like why you would want this extra step of having a paymaster instead. So in more detail, off-chain, so same steps as before, but now additionally, we also have to check that the paymaster adheres to the EIP. And for that, we also have similar restrictions, opcode restrictions, storage access restrictions. However, again, or like I just mentioned, if the paymaster has a stake, there's some relaxation to this. And yeah, checking the paymaster stake inside of the entry point contract is something that is done off-chain. It's not done on-chain, I believe. And then similar as before, I'll just go through it again. So the user op gets picked up by the bundler. The bundler sends the bundled user ops into the entry point contract, which then verifies that every individual wallet is can execute these user ops. Then it also verifies that the paymaster is willing to pay upfront for the gas. So that is step 4. That is the paymaster validation. In step 5, the user op is executed. And in step 6, the paymaster post-op is executed if the paymaster so desires to have this executed. Yeah, so some security considerations for the paymaster. The paymaster requires the post-op execution to be guaranteed. There are some cases where, or in the example that we had before, you could think of a case where the paymaster sees that Alice has given enough approval to the paymaster, and then the user op is executed, and in the post-op, the paymaster actually receives the payment from Alice wallet, and perhaps swaps that token on Uniswap for the native token and is thus reimbursed. So yeah, it's required for reimbursement, and if the one thing that could go wrong is that, as I just mentioned in this example, so that's why I have this graphic up again, is that the paymaster in step 4, where it validates that the paymaster is willing to sponsor the transaction for Alice, in step 5, since step 5 is unrestricted, Alice wallet can do anything without any restrictions. Alice could, like as a simple example, revoke the token approval, and then in step 6, suddenly the paymaster is not reimbursed anymore. And if we had this kind of case, this would obviously be a big security issue, and this would mean that anybody could simply drain the paymaster. So that means if the paymaster post-op does not succeed, we basically have to revert the entire transaction. But what we first do is, so going back to step 4, the paymaster accepted to sponsor the user operation for Alice. In that state, everything was still fine. Step 5, the user op is executed. And in case something changed on chain, which disallows executing step 6, then we just revert the user operation in step 5. So that's why step 5, the execution, is packed inside of another call context, which can be reverted. Then we basically go back to step 4, ignore the user op, and go directly to step 6, where the paymaster receives the payment. So that's the idea behind that. And there's also a paymaster reputation system, which I'll go into in a bit, and we want the paymaster would like this to be manipulation resistant. So some considerations as the bundler. The bundler now, instead of relying on the user to pay or to reimburse him, the bundler now relies on the paymaster instead. That means, well, I mean, for Bob, a user op revert is acceptable. However, I just went into detail on why a post op revert must revert the entire transaction. And this is bad for the bundler because this means that Bob has paid for the whole transaction, which is now getting reverted, and this is Bob's loss. Yeah, so this basically means, or this alongside with the fact that a paymaster, since many different user operations can specify the same paymaster, a paymaster is now able to invalidate multiple transactions or user operations. And that's why we have these similar opcode and storage restrictions applied to the paymaster. However, these are relaxed through a paymaster stake. And just a small info on or more information on the stake. The stake is something separate from the deposit. The stake is, there's no slashing inside of the protocol. The stake is simply, can be thought of a time-locked deposit. So to withdraw the stake, it takes a certain amount of time. However, there's, again, no slashing. It's not enforced by the entry point itself. This is something that needs to be checked off-chain by Bob. Yeah, as I mentioned, relaxation through a stake or alternative mempools. But this also shows that we have a need for a paymaster reputation system. So if there is such a malicious paymaster, then Bob, if he doesn't want to constantly send invalid or reverting transactions using the same paymaster. That's why there is this off-chain paymaster reputation system, which is updated locally for Bob in his bundler software. So this is not something that is on-chain. Every other bundler also updates this locally, and if another bundler sees reverting transactions on-chain, then this is used as information to update the reputation of that certain paymaster and potentially ban him. But as I mentioned before, it's an exponential moving average, so it's like not a hard ban. And the reason is that we have kind of offloaded the responsibility from the user to the paymaster, because a user that doesn't have any stake or deposit can't be held accountable. So security considerations for the user, again, user just requires trust in smart contracts. So the paymaster has to execute faithfully in the entry point as well. This is good for the user because the user can hopefully only trust immutable smart contracts, which the user can verify and inspect. So I'll go into some additional features and final thoughts here. So I talked about the initial wallet creation. So the opt.init code contains the factory address and the init code to be executed. And because the factory address is another entity in the system, which also many user ops could specify the same factory. And again, the factory could invalidate many user operations. So that's why we need similar EIP restrictions to be applied to the factory, but also to the wallet constructor, because the factory creates a new account and which is a new address, and inside of that address we have the constructor running, which is new code, and we need similar opcode restrictions there. We cannot use any block timestamp or context-dependent opcodes. And the factory contract can only use create2, so it can the account creation cannot depend on the factory contract's nonce. Okay, I see there's another question. The question is, where do we find all infos related by the stake? What is the minimum to stake, etc.? So that's defined in the EIP, I believe. You can just read it up in the ERC. I'm not sure if I've read specific values myself, but this could also be depending on the mempool that you'll use, and so depending on perhaps the bundler software. Another question, is the storage rule access only for verification? Yes, it is. So only during the light verification phase, we want to apply these storage access restrictions. It would be quite limiting if you had these restrictions inside of the execution phase. That would heavily limit the amount that you can do on chain. And again, the idea is only we want this kind of almost pure verification phase where you could think of it as like only some kind of like signature validation. However, again, like there's some use cases where we would want to relax this a bit, and that's why we have some like storage access rules. Also, for the example that I gave, that the paymaster might want to access some kind of storage related to some account. So moving on, there's also the feature of signature aggregation. This is a useful feature for rollups so for aggregated signatures, we can only check one signature instead of n. So n signatures are aggregated to one signature. And this is great for rollups because rollups have to post their call data onto Ethereum layer 1. And a big amount of the gas spent for rollups is used on call data. So if we can compress that call data, that's a big win for gas on rollups. Again, the aggregator. So aggregator is a smart contract on the rollup. This is another entity and requires similar EIP restrictions. And just as an implementation detail, the wallet can respond with the aggregator address in the verification step. So let's look at some of the gas costs. The token prices of Ether have changed quite a bit, but we see that creating an ERC-4337 account is $20, $30 something, which is not ideal. It's pretty gas costly. Simple transfers and ERC transfers, ERC20 transfers, I believe, are around 4 to 5 times more expensive on Ethereum. On Polygon, we see that the gas costs are reduced by quite a lot. Also, Optimism, so rollups and other chains can kind of benefit from this ERC. It might be a bit too expensive for Ethereum, but yeah, this is still like a great testing ground. So this is a Dune Analytics graphics created by Nifty Table. John Rising also has a bunch of great ones, and this shows the monthly successful user ops by chain. It's pretty interesting to see because the last time I checked it in April, things have changed quite a lot, and we see that Polygon is leading in most successful user ops, but the rollups such as Optimism and Arbitrum are also picking up. And we also see there's a lot of bundler software being worked on by Blocknative, Biconomy, and StackUp. So I see one more question here. Someone's saying they're slightly confused. When is the bundler getting paid, and is everything happening in one transaction? No, or I'm not entirely sure what you mean by one transaction. So Bob submitting the bundled user ops, so an array of user ops for different smart contract wallets executing different calls, that's all one single transaction by Bob. So one single Ethereum transaction as we know it. However, that one transaction, as I mentioned, contains these bundled user ops. So many individual user ops, and a single user op is executed inside of a smart contract wallet. However, or maybe to go back again, Bob executes or calls entry point.handle ops, passes in this bundle of user ops, and then for every single user op, we have these two phases. We have a first step of a light verification, and then after that has succeeded, we have the heavy execution, which has unrestricted storage access and opcode use. Yeah, hope that answers the question. And let's have a quick look at account abstraction in layer 2s. So for Optimism, we saw they early on introduced new opcodes for some basic account abstraction. However, the OVM decided to revert back to EVM equivalence for security reasons. And there was one interesting project called Opclave, which I think was created in a hackathon for ETH Global. It's called Opclave Apple Sign. It basically allows Apple Face ID, Touch ID signatures to be verified inside of a smart contract in the context of ERC-4337. StarkNet and ZK Sync both have account abstraction, and the account abstraction is heavily inspired by ERC-4337. However, there do exist some differences. But yeah, it's good to see that we're all kind of working on the same specs. So to give some concluding thoughts, this ERC is still under active development, even though it's marked as ready. Compared to the last time I checked, for example, the nonce management was handled by the individual wallets. Now the nonce management is all handled by the entry point contract itself. So there's still some changes that might happen. Also, as I mentioned, getting all of these specs for minimizing the denial of service attack surface is quite hard, and I'm pretty sure we'll see some changes there. The good thing is this ERC does not require any hard fork. It can be implemented today, and it is implemented today, and it is being used today, and it's being iterated on, which is great. There's some trade-offs to consider, however. It does have a high amount of complexity. I won't deny that. There are many different entities, many things to consider. For some people, it does seem overly complex, and it introduces new attack surfaces. And for the user, it also requires this additional trust when sending transactions, trust in bundlers, trust in paymasters, and other entities. There's some limitations to this EIP. As mentioned, the gas cost can be prohibitively large. This is not native account abstraction. Many people really want native account abstraction, and it's still not here. However, as I mentioned, for getting the specs right, I think this is a good step in the right direction. It doesn't replace some of the features that many protocols have wanted from EIP 2771, which is like subsidizing gas for users. Yeah, so these are some additional resources that I used. Yeah, some great Dune tables, some good blocks by StackUp and Nethermind. There's also an audit on a current implementation done by OpenZeppelin, and if you want to follow some people and learn more, there are these accounts that you can follow on Twitter, for example. It's not all of them. There are many more that are interesting to follow, but just to name a few. And yeah, if you'd like, you can stay in touch. My Twitter handle is LoveTheWired, and I hope you enjoyed the presentation. And I'll see if there are any more questions. Okay, so there's one more question. On the execution phase, we are using gas, whatever value was given in the verification part. I'm not entirely sure I understand the question. So the gas, which is used inside of the execution phase, it is, let me go back. Oh, that was too far back. Yeah, okay, so here we see the user operation, and we see that there is a field for call gas limit and verification gas limit. So call gas limit is the gas limit for the main execution call, where the contract accounts has this heavy execution phase where it has no restrictions whatsoever. So you as a user specify how much gas you want to have in that context. Then there's also a gas limit for the verification step, and basically user you have to pay. Well, in the end, you just pay for what you use. But in the simple relay flow where you pay upfront, you have to pay just like with Ethereum, you pay upfront for the maximum gas, but in the end you just pay for what you use, so you're refunded. So in this case, you would pay you would have to be ensured that you have the funds for the verification gas limit plus the call gas limit, and then there's still some additional details like you need. You can also specify pre-verification gas, and because there's some overhead. Okay. Another question is it more expensive to use account abstraction because you are paying for the verification plus the bundler fee? Yes, it is definitely more expensive because of all these additional operations that are run on chain. So basically the verification, yeah, exactly. The verification, the bundler fee, perhaps the paymaster also has a fee. And then there's still perhaps signature aggregation or whatever. But for signature aggregation, perhaps the fee is split up by the end transactions, so that might not be so heavy in the end. But one interesting thing that I heard was the idea that these bundlers will basically all be run by people who are incentivized to create their own order flow. So you could think of this as like MEV searchers that order the transactions so that they can perhaps extract some value out of that. And in that case, perhaps there is no need for an additional fee for the bundler. But one more thing I wanted to say, the transaction gas cost that I showed, let me go to that slide. So the gas costs here, I'm not entirely sure, but I'm pretty sure. I assume that these are without any bundler fees, because those can be arbitrary. So these are, I assume, purely execution costs. So on top of that, you could imagine some kind of bundler fee or paymaster fee. But then again, it could be that this would be taken over by entities that can kind of profit off of or a transaction ordering. Okay. Yeah, I guess that's it. Are there any more questions? Okay. I'll yeah. I'll just wait a few seconds, see if there are any more questions. Okay, well, then I guess that's it. Like I mentioned, you can catch me on Twitter. I hope you enjoyed it and have a good day.